We are now doing October, November 2025, variant 41. We have completed question 1 and question 2. So now we are going to question 3. Define gravitational field at a point. Okay, without looking at your answer, try to define for me.
wait. Question 3, question 3. Okay, wait.
Question 3, 1 and 2 we have done already.
Gravitational field at a point. Force per unit mass.
Good. Force per unit mass.
And
There's your 1 point. Figure 3.1 shows an isolated point mass M. Point P is a distant x from the point mass. By considering the forces exerted by the point mass on the test mass, or mass M placed at P, derive an equation for the gravitational field at G at P in terms of mx. Identify any other symbol you use. So you define and you use a definition to derive. Right? There's your mathematically your definition. Force per unit mass. So you put a test mass there. Find the force on the test mass. Divide by the test mass you put there. Then the force is Newton's gravitational law. Okay? Gmm over x squared. This m is this m. So m and m can cancel off. So we've got Gm over x squared. Okay, mark yourself. G is the gravitational constant. The one you have to identify because these are the new thing they didn't mention in the question. Right, we have derived this equation. On figure 3.1, draw an arrow to indicate the direction of the gravitational field at P. Where's the gravitational field at P? Up, down, to the left, to the right?
left.
Okay, good. Just draw that, that's all. Point Q is a distance x over 2 from the point mass M on the opposite side of mass from P as shown in figure 3.2. Compare the gravitational field at Q with that at P. Okay, what's the difference between P and Q?
Opposite direction.
Okay, opposite direction and 2 point.
Field strength at Q is higher than field strength at P.
Give the magnitude.
Must I state the value? Must I state how many times?
Yeah, you have to say every time because it's very clear. Very clear, you can calculate. You are in opposite direction, that's your first mark. Field strength at Q is 4 times the field strength at P. Right? This is half of that. Because of the square, it becomes 4 times. Okay.
Okay.
Two identical isolated uniform spheres X, Y, each have radius R. The center of the sphere are separated by a distance L. Point P lies on the line joining center x and y and is at a variable distance x from the center of the sphere x. Right? That's your distance x. The gravitational field strength at the surface of each sphere is G0. On figure 3.4, sketch the variation with time with variation with x of the gravitational field strength G at P between x equals to R and x equals to L minus R. Right? That means here, from here to there. Right? Radius is big R, radius is big R of the sphere. Okay, the gravitational field is different direction. X would be the blue one, Y will be the red one. So you can see that at the middle point, because both of them have the same mass, and the midpoint there will be 0. And then in that distance there, the gravitational field due to X is greater than to Y. So it should look something like that. Line at R minus G0. That is what they are looking for. Ending at that. As long as your curve is that way, you get your first point. Line passing through L half there, that point there. Okay, so you have to draw perfectly lah. Very difficult to draw using Microsoft Word. Curve becoming shallower from L equals to from R to L over 2, right? Shallower and steeper. So you get your 3 mark if you got that correct. That's the marking scheme. Any comment? Anything not clear? Okay, take the absolute 0 on the Celsius temperature scale. Yep. What is it?
Absolute zero.
Celsius scale, Celsius scale.
Oh wait, this one is like minus 273.15.
1.5. Be
I
there.
put 0.2.
Calculation using PV equals to nRT. You don't use 273 only. But it must be precise. 273.15. Thermodynamic temperature scale, give a unit with your answer. Okay.
0 Kelvin.
0 Kelvin. A sample contains fixed amount of gas. The gas has a pressure P and volume V. That's your PV against KT graph. On figure 4.1, shows a variation of PV with KT for the sample, where K is a Boltzmann constant. State what is indicated about the nature of the gas from the variation in figure 4.1. Yep.
Ideal gas.
PV equals to NKT. Right? Ideal gas. Determine the number n of molecules by the gas in the sample. How do you determine n? Yep. How do you determine the value n?
PV equals NKT.
PV or NKT, so you can just take a point, or take a gradient, either way, right? And it's gradient. When you find a gradient, I usually
Gradient.
prefer to take the last point, easier to read, right? Remember that must be there, don't be careless. PV is 270 joule, so that's your answer. Use your answer in B part 2 to determine the amount of gas, the amount of N of the gas in the sample, right? That is your formula sheet. So we have calculated capital N. So small n is just your capital N divided by Avogadro's number, 0.056 mole. The root mean square speed of the molecule of the gas is 1900 when PV is equal to 270 joule. Determine the mass M, mass in atomic mass unit of one molecule of gas when U is a unified atomic mass unit. What formula should I use? Yep, what formula should I use?
The kinetic energy formula.
If you forgotten, you can use this formula. Formula. PV is given. You want to find M. Take 3 across there. Take N down. Take this one down. This square split down. And then you have to PV is 270. Then N. Then you have calculated previously. Then mean square speed. This should mean square speed. So you square that. So that's in kilogram. You want atomic mass unit. So want to go to your data sheet. My atomic mass is 1.66 and 10 to the power minus 27. So you divide like that. So it's for atomic mass unit. Okay. Anything now clear?
Okay. Okay.
Define electric potential at a point. Okay. How will you define it? Yep. How do you define it? You tell me, if possible.
Work done per unit charge in moving positive charge from infinity
Okay. Work done for unit charge in
to the
moving
point.
positive charge from infinity to the point. Right. That's your formula sheet. Hydrogen atom may be considered to consist of a proton and an electron separated by a distance of 120 picometer, shown in the figure. The two particles may be considered as point charges. Point P lies on the line joining the electron and proton and is at a variable distance x from the proton. Show that the electric potential V at point P at 10 picometer is equal to 130 volt. Right? Use the definition formula, this formula. Right? This formula. There are two of them. Right? I take the charge up. Both of them have the same charge. So that E and E taking it out, that's your E. 1 over 4 pi epsilon naught is the one for 4 pi epsilon naught. Okay, or you prefer your own way, you can use your own way. This is in the formula sheet also, this value. And then 1 over R is left. 1 over R for this X there is 10 into SI unit. And then if this is 10, this is 110. 110 into SI unit. 130 volt. Okay or not? Anything not clear?
Yeah, okay.
Okay, calculate the two significant figure V when X is 30. This one they want you to sketch the graph lah. So that's why they ask you to calculate the value. Now same formula. Take the common factor out. 10 to the power 12 can take out from each of them. And then if this distance is 30, that distance must be 90. That's what you get. So you get 32 volt. On figure 5.1, draw a cross at one position other than infinity where the electric potential is 0. Where is it likely to be 0? Yep. Where is likely to be 0? Can speak a bit louder. Cannot hear.
Both
Both of them have same charge, same magnitude of charge. One is positive, one is negative. There, one is positive, one is negative. So at the midpoint, midpoint there, it will be 0. Right? That midpoint there, roughly there. Then they ask you to calculate, they want you to sketch the graph. So important the value are calculated must be plotted on the graph. Right? At 30, at 10, same, symmetrical. And then at midpoint is 0. Midpoint is 55. Something like that. Okay or not? Mine is very poorly drawn. This one doesn't pass, the curve doesn't pass through here. But that's the best I can do. But this point must be correct. We have calculated it out already. 130 volt. Same as this point. 130 volt minus 130 volt. Can? That's what the marking, that's how you are marked. Okay or not? Okay or not? Mean at this point, there's 130. At this point, 130 also. The curve becomes shallower. V naught at 60 there. And then getting steeper, steeper. After x equals 60, curve passing through 30. This point at 30, 32. And then 90, 32 also. Right? 30 from here and then 30 from here, the same, symmetrical. 32 lor. So 32 is 4 square lor. Okay, now any query?
No.
Two parallel plates, capacitors C1 and C2 are connected to a supply and has a potential different Vs. The capacitors may be connected in series or parallel. The supply,
5 equals Q1 Q2.
is it a bit louder?
Series Q1 equals to Q2.
That's from your formula sheet. So your answer should be, right? This is in series. This one is in parallel, connected to the source Vs. The relationship between the charges, what should it be for this part?
4 equals Q2. Q1 equals Q2.
Q1 equals Q2 equals Qs. Relationship between potential difference Vs equals to V1 plus V2. How about here?
Q1 plus Q2. Okay, V1 equals V2.
Huh? What should it be?
V1 equals V2.
What should this one be?
Q1 plus Q2.
Yeah, this one Qs is Q1 plus Q2. But about potential difference? Vs equals to what?
V1 equals V2.
No, V1 equals to V1 equals to V2 lor.
Huh?
Okay?
Yeah, V1 equals V2.
Hmm.
Uh,
And also capacitor or capacitance 470 microfarad, store energy of 17 millijoule of energy. Calculate the PD across the capacitor. Right? They give you energy, so you use energy formula. Right? V, take a 2 across, take a C down, then square root it, and put in your value. 2, this is the milli, so change it to SI unit. C is 470, change to SI unit, calculate out 9.0 volt. Calculate the charge on the capacitor. Q is CV. Okay. Any comment?
no.
No. Okay. We are all right. The capacitor is now connected in parallel with a capacitor of capacitance 180 microfarad that is initially uncharged. Determine the total energy now stored in the two capacitors. Okay, that is your initial state. You connect it to a battery 9 volt. Then after that, you connect another capacitor here, 180 microvolt. Determine the total energy. So Q equals CV. The charge is conserved. Charge doesn't disappear. It will just distribute. So the charge will initial in here. It will move until both of them have the same potential. Then it will stop. Initial charge is that one there. From here. Equals to final charge stored in capacitor. So initial charge is 9. We use Q equals CV. 9 times 470 10 to the power minus 6. Then finally the potential is the same. V take it out. Right? Or they are in parallel. So 470 plus 180 10 to the power minus 6. 6.5 volt, and use the total energy formula. Total capacitance is their parallel, and then V 0.5 square. Okay or not?
Yeah.
Stop me if you need any clarification. We are looking for total charge on change. We are looking for this step there. One mark. Total charge. Total charge there. You're looking for this step. And then after that, they use charge rather than use potential difference. Doesn't matter as long as you get the same answer. It looks like for October, November paper, they tend to come out Faraday's law lah. Okay, stay Faraday's law.
Oh,
Stay Faraday's law. Can remember?
yeah.
Can?
I
Induced
need to refer to
direct
answer.
proportional to the rate of change of magnetic
Yeah.
flux linkage. An aircraft is flying horizontally at a constant speed v, show the diagram here, through the Earth's magnetic field as shown in figure 7.1. Right, this is you look from the top there. Right, view from above, view from the side. At the location of the aircraft, the vertical component of the Earth's magnetic field is 38 microtesla from here towards the ground. The distance between the wind tip P and Q is 68 meters. Written there. As the aircraft moves through the magnetic field, the electromotive force of 0.554 volt is induced between the wind tips P and Q. Calculate the magnetic flux cut by the wings of the aircraft in the time of 15 seconds. Give a unit. Right, you got 10 more minutes. Use your definition. That's EMF is induced equals to minus d phi dt. Right? Cross multiply. Want to find flux. We are given EMF. EMF is given. So EMF times time, cross multiply. Right? 0.54 volt, 15 seconds. So 8.1 watt. Weber, sorry. Weber, not watt. Calculated that. Determine the area of flux cut by the wing in 15 seconds. Okay. Use the formula. Flux equals to VA. So area is flux over B. 8.1 we have calculated. B is from the question paper. 2.1 times 10 to the power 5 meters squared. Use your answer in part 2 to determine the speed of the aircraft. Right? That's the area. So it's this length times the speed times time to get the that distance. Right? Area is speed times time times width. Right? That's your width, speed, times time becomes that distance. So speed is take L and T down. A is a calculator. L is 68. T is 15 seconds. Right? 15 seconds. Okay or not? Use Lenz's law of electromagnetic induction to explain which of the wingtips P and Q is at a higher induced potential. You don't have to use right hand rule. Right hand rule is not taught at all. By right, you use right hand rule faster, but they don't want you to use right hand rule. They mean right hand rule. So how do you reason it out?
The opposing force due to the induced current in the wings must be backwards to oppose the forward motion.
Okay, then
And then current flows from negative to positive inside an EMF source. So the P is higher. Oh, P has higher potential. It's at higher potential.
okay. Opposing force due to current in the wing must be backwards. Right? Backwards there. Opposing force. Then they use Fleming's left hand rule. Current in the wing is from Q to P. Make sure you know how to do that. Left hand rule. There's your field going into the page. There's a current. And then there's your force. So the current is from Q to P. Right? But remember this is a back inside a battery. The current is from negative to positive inside the EMF source. So P is a higher potential. Remember that we are looking into the battery itself, not outside the battery. Outside the battery is positive to negative. Inside the battery is negative to positive. The current is flowing from Q to P. So P is a higher potential. Can? Okay or not?
Okay.
Okay, say what is meant by a photon. Yep. Packet
It's
or
like
quantum of
a
energy
packet.
of electromagnetic radiation. 2 mark. A station nuclei
The marks
uranium.
come for what?
Say again.
The marks come for what? Packet. I mean,
You can either call it packet or quantum. No? Packet or quantum of energy. That's 1 mark of electromagnetic radiation. No? Right? This is memory work. Memorize. A stationary nucleus of uranium-238 undergoes alpha decay to produce a nucleus of thorium-234. The kinetic energy of emitted alpha particle is 4.2 mega electron volt. A gamma ray photon is also emitted during the decay. Assume that the rebound kinetic energy of the thorium is negligible. Figure table 8.1 shows the masses of the nuclides involved in the decay reaction. The mass of uranium-238 nuclide is missing. It's missing. Right? Have a picture in your mind of what's happening. Right? And then remember that this one you need to remember, same as the charge of the electron. This one can get from data sheet. Okay, it's part of the table. Calculate the mass in atomic mass unit of uranium-238. Give your answer in 5 decimal places.
E
Convert
equals mc square.
the energy to mass equivalent. E equals mc square. Delta M is delta E over C square. Right? Delta E is this one. Change it to joule. 4 by 6 and 10 to the power 19. 10 to the power 19. And this is your speed square. And you divide by 1.66. You're going to convert. This one is kilogram. I want to convert it to atomic mass unit, so you divide by that from the data sheet. This one. So you get 0.04577 atomic mass unit. Mass equals the mass of product plus energy equivalent. Right? Mass of product is the mass of product plus energy equivalent. Okay.
Yeah.
1 minute now. Determine the value of wavelength of the gamma ray radiation emitted during the decay of uranium-238 nucleus. Okay, that's what is given from the previous question. Right, that's what we are using. Right, replace your F with lambda. You got HC over lambda. So lambda is take the E down, cross multiply. H is from the data sheet. C is on data sheet. And then this one minus that. And 10 to the power 6 mega. Then times 1.6 and 10 to the power minus 19. Change it to joule. Can. Anytime will cut off. In practice, the rebound energy of thorium nucleus is not negligible.